Okay, lecture number 3 here. We're going to take a look at coal and the different types of coal. You probably need to be somewhat aware of this. It's looking at the comparison between moisture and heat content. Something they have up in Ireland that they use as a cheap fuel source is peat bogs. It's the very beginning state of coal, and over a long period of time, pressure and heat, this stuff condenses, compacts, and eventually turns into anthracite, which is like a hard coal. We don't have a whole lot of that. Primarily what we use here in the United States is bituminous coal. We have a whole bunch of that stuff, but it does have some impurities in it, sulfur content. So when you start talking about acid rain, that's the sulfur content. So when sulfur goes up into the atmosphere, SOx and NOx we happen to call it, but if we're talking about sulfur, we're typically talking about SO2 and SO3. And just to make the comparison, we'll just call it X instead of 2 and 3. So it's called SOx. When that mixes with water in the atmosphere, you typically will end up with H2SO3 or SO4, which we call sulfuric acid. So that is one of the problems in using coal in our power plants. But typically, a lot of our power plants have things called sulfur scrubbers, which take a lot of that out. We'll probably mention that some other time. And this is just the formation of how we get this coal in different parts. So you have a peat bog, and then over time, as far as pressurizing, it turns into anthracite. Looking at the amount of coal, we see that we have a whole bunch of it. Notice the comparison to who has it. Obviously we do, China, Russia, but we're also really big users of coal. So the 3 biggest users of coal would be China, US, and India. And that makes sense, of course, based on population and our economy. We're really big users of it. But Russia, even though they have a lot of it, they don't seem to burn quite as much. One, they don't have quite as many people. And 2, they also have a lot of oil. So I would imagine they're using quite a bit of that too. And they use nuclear as well. Okay, the bad thing with using coal is that it has a lot of carbon dioxide. And of course, that is a greenhouse gas. Something else that we can do with coal is we can convert that into liquid materials, synthetic natural gas. That is, if you're looking for a different target usage. So if you want a gaseous product that you can transport instead of transporting the coal itself, if you want it for transportation in your car, that would be a good reason for doing this process. But of course, whenever you're making this transfer of energy from one energy source to another, you're losing some of that content, which if we haven't mentioned it yet, we'll go ahead and do it right now. The second law of thermodynamics states that whenever you change energy from one source to another, you're going to lose some of that total amount. So if you had 100 units of energy, now you have some lesser amounts, 90, 50, whatever. Cogeneration. The idea of this energy source is trying to maximize the amount of energy you're taking out of a energy source. So as I just mentioned, based on the second law of thermodynamics, you lose energy when you're transferring, say, for example, the heat content to coal in the electricity generation. So one of the ways you can try to capture some of that energy is to use that heat content to heat up something, whether it be water or some other resource. But generally, it's like a water source that you could transfer that energy, heat, to something else. So that's one potential use of it. And we have a little video that goes along with that, which we will not watch. You can watch that on your own. Energy production problems, and this is what we'll mention for the first time in the lecture, the second law of thermodynamics. So the first law states that energy cannot be created nor destroyed. The second law says a few things, but what we're going to focus on is when you're transferring energy from one source to another, that you're going to lose some of that energy. So again, if you had 100 units in coal, by the time it actually gets to your house, you have probably less than 10% of the original energy content that you started with, which is awful. But because we have so much coal, it's relatively cheap, and we're not too concerned about it. Efficiency. There you go. You'll be better off taking the coal to your house and burning it in your furnace, as far as heat content goes. Just mentioning it here, 35% as far as the burning and turning into electricity. This is a real quick demonstration or graphic that kind of shows the idea of how they generate electricity, bringing in the coal, the process of pulverizing it, putting it in a furnace, heating up water. This is how electricity is created. Turns a turbine, turns a generator, and electricity goes out the lines to your house. So, switching gears, moving away from coal, we'll talk about nuclear. Nuclear energy primarily uses uranium-235 as its material to heat water. Everything else, as far as electricity generation, is the same. It's the fuel source that goes into it. So one of the things I know it's going to come up one time or another is it's uranium-235. 239 is the most common isotope of uranium, but 235 is the one that we focus on, whether we're using it for heat, electricity, or you're making bombs. But we're generally using it for heat. So this picture looks a little different, but the guts of it are pretty much the same. You're heating up water, you're creating steam, it goes in, turns a turbine, and that turns a generator, which creates electricity. One thing just to kind of notice here is within the system, here's our core where we have our nasty radiation. It's heating up a liquid, which goes in and heats up water in here, which of course turns into steam. Now these two systems are not at all connected between the core and this water that's being heated. They're not connected at all. So I have steam going out, turns a turbine, but that water or whatever solution mix is also not connected to this condensing water. This is water that would be like in a river or lake nearby. This water is third string along the way, separated from the core. So the potential for this water being pumped out from the river or lake or whatever going into the plant is third string separated from the core itself. So the potential for contamination is very, very low. That is always a misconception about nuclear power plants, is that the radiation is going to make you sick. Yeah, if you have a Fukushima, that could be a problem, but generally that's not the case. So this is kind of showing the guts of a power plant, nuclear power plant, looking at some of these control rods which are in there, the water bath after the fact. Very interesting. Notice how it says after 3 to 4 years we actually have to take the fuel rods out and move them. They're not efficient any longer. In comparison, so these fuel rods after 3 to 4 years, in comparison, coal plants require 80 rail cars a day on average. So just compare. The energy content in uranium is huge comparatively. Doesn't mean the nuclear power plant's all that efficient though. So it's just showing some of the control or the storage tanks for some of these fuel rods. And this is one of the real big downsides, is this waste material never goes away. No, you don't have to replace it very often, but again, this waste material is there forever if you consider thousands and tens of thousands of years forever. So, your book goes into a couple reasons why we don't do this anymore. We haven't built a nuclear power plant in the United States since 1978. And there's a couple big reasons why. We'll break it down to two. One is the cost is incredible. It costs billions of dollars to make one of these plants. We had some plans ready to go, and I don't know if they broke ground or not just a couple of years ago, but I believe they stopped once the whole Fukushima thing happened because of the fear, which is the second big ticket item. People are kind of afraid of nuclear power plants, and for pretty good reason. I think the bigger issue is necessarily terrorists or natural disasters. It's more about this cost and this subsidized cost that comes from the government that hides the true cost of what a nuclear power plant costs. It's very, very, very expensive. You'll be much better off putting that dollars into something which is more sustainable. All right, another good place to stop. We'll pick up the fourth lecture in just a moment.